Welcome back. Well, that was a long delay. Hope we can make it up for it. Just to be clear, we did have quite a few off-the-record gatherings. We talked about different topics we could possibly cover, and Stateful Orchestration won by a large margin, like a really large one. So it's a big episode for me personally, not only because it's after a long delay, but also because I think I can talk about the problem of stateful orchestration so that it builds on top of many other things we covered before. So we will consciously not touch event sourcing today. We could potentially go there in some other episode. But I honestly believe that stateful orchestration can be viewed as the extension of the problem of the task queue, distributed task queue. Because once you go from tasks to workflows, and once those workflows become stateful, you sort of solve the main problem of distributed computing, if you do it right. And I'm also fully aware a lot of people come here because it's decent-ish interview prep material for SysDesign. So while I'm not gonna give a lot of direct advice, two things up front. One is I will cover something that is from what I know, fairly common interview problem today as an exercise. And two, hopefully by the end of today, but by the end of the episode, like you and the listeners / readers / watchers would have some idea how to approach problems, from which angles they look easier, so that at the end of the day, everybody benefits. You can solve better problems and talk yourself out of different holes and present your solutions better. With no further delay, the plan, which by the way already has changed, but the plan was that I'm going to spend some time talking about the problem statement. What is it exactly? What does it mean to solve stateful orchestration? And I'm going to talk for a lot about how different sub-problems that exist in the world of SysDesign map into stateful orchestration, so that once you understand how to think of them, once you can reason from them, you're most of the way there, both to stateful orchestration, whether you need that or not, and more importantly for other sub-problems that do emerge quite often in the realm of SysDesign. And I wanted to put some time aside to talk about some potential generic solution, which I think is a super fun topic. But during the preparation, I'm almost positive we're not going to have time for that. So think of that as a teaser, because in the interest of actually recording shorter episodes, let's hope we can get there for a bit and keep you entertained enough for the next ones to come. So the problem statement for stateful orchestration is surprisingly deceptively simple. We sort of want to be in the world where we can write the code as if it's deployed on a single machine. And it's a common question that is often asked, like in interview prep and other meetups and events. Don't we get faster computers every day? Why do we even need all this SysDesign stuff? The standard answer, of course, is even if your single machine can hold everything, there are at least three reasons why you need distributed systems. One is availability. Stuff tends to die. The other one is redundancy. What if your data center is offline? What if someone is about to steal your data, like hard drives? You want to make sure your service is up and running. And the third reason is regulation. Sometimes you, by law, to operate in a certain country, you have to make sure your data lives there. And of course, you want your service to be available in more than one country, which means you have to design distributed systems surprise. So at the same time, even though we have to build things so that they actually run on multiple locations and multiple machines, multiple node servers, to me it's the same term. At the same time, in terms of writing the code, a lot of things are dramatically simplified if the engineer who writes the code can afford to make the assumption that this code is going to run on a single machine. Because think of all these bolded problems that arise. If you have multiple databases, synchronizing their transactions between them is super hard. But if you have a single machine, you can have a single database, and life is easier. If you have caches that could be out of date, if it's all magically up to date on a single machine, because it is, life is easier. All those dual writes, dual reads, so that different parts of the system are out of sync, well, if you have a single machine, that's a non-issue. Nothing to backup and restore, because ideally, if you have a single machine-ish deployment, the infrastructure, the underlying frameworks take care of that. The dreaded exactly once question that is usually super difficult on a large scale. In a single machine, you're good, and the sharding part topic, you just ignore it. So in a way, stateful orchestration covers the problem from both ends. So like bottom up, if you have I know it's hard to phrase clearly, but if you could do the task queue problem effectively, it's gonna grow into orchestration stateful workflows, and you're good to go. On the other hand, top down, once you know how to build stateful orchestrated systems, you have solved every single problem in SysDesign, because you know exactly how to build the code as if it is built for a single machine, but is executed by the environment that runs on multiple machines, concurrently, consistently, and whatnot. So it looks like Holy Grail, and let's see what the issues with it are. I'm going to go on a philosophical detour for short to mid-term. So there are requirements, right? There are function requirements, and there are meta-function requirements for software. And in order to pick the right approach to build some software, we need to decide on the higher order requirements. For example, how many people are going to develop this software? How many engineers do you need for how long? It's one thing if it's a very niche product with clear requirements to be built within like half a year, just ship once, run forever, like the Mars mission 20 years ago. It's a totally different thing if you want to build like a Google search engine that is it's a product destined to be developed for decades by thousands of people that needs to be evolving, growing, like languages changing, teams changing, but the product has to evolve. Now, how well defined the problem statement is, sometimes if you know for a fact what is there to build, if you can write down the acceptance criteria, just design so that it fits, the solution fits this criteria, and you're good to go, that's a perfect world for engineers. Most often, it's not the world we live in. Most often, we need to live in the world where you build something and then you also extend it later on, and you have to maintain it for a long time. And also, I keep talking about this like in different events. You have performance-sensitive systems where it's super critical, like high-frequency trading, that your system responds within a certain number of hundreds of nanoseconds, literally. And if you do not abide by this requirement, you're too bad, sorry, you're out of business. But there's also feature delivery pace, where it's okay if the team is not too fast to launch things, but at scale, if you look at like years and years and years of evolution, features are being added by different teams, and the product itself evolves, even though the margin of pace of development for each particular individual feature is super low. And the point I'm trying to make here is that in the industry, most often we are in a totally different realm. The industrial software design has to do with no tight requirements, no time boxed, and you have to design for the large company developers, coders, people, maintaining the software over time. And that's exactly where standard boxes come into play. That's why we do SysDesign. I'm not trying to say that SysDesign is useless. I'm trying to say that if you are hired as part of like a SWAT special ops team to build something non-trivial under tight constraints, you would reason same way as you do on a proper design interview or like on a whiteboard session in a big company. But you would make totally different trade-offs. You would take different routes. But at the same time, knowing that, it's super useful to know how to design systems in the real life, not just to pass the interviews, but also because that's how people tend to communicate, and that's a good thing. You want to design your software so that regular engineers, so that you can like hire a bunch of mid-level people and junior people into your team and make sure they help you deliver software. That's why we talk about all this stuff. Even though we understand that on a high level, it's not necessarily how moonshots are built. So that's why in practice, generic solutions are awesome, even though they are less effective than peak effectiveness for most particular problems. Over time, developer time is more important than machine time, and real life problems are evolving. So let's build over standard solutions. Let's build on top of standard solutions. And I thought long and hard how to best put this into one sentence, and the sentence what is bolded here on the slide. The metric to optimize for is the pace of developing software at scale by mere mortals. So by at scale, I mean you need to be able to grow the team from 3 people to 30 to 300 to 3,000. And by mere mortals, I mean these 3,000 people would, there's a healthy pyramid, there's a healthy distribution of levels. Like you're lucky if 3 of 100 would be like staff plus levels, and more than half would likely be mid-levels and juniors. And that's normal and healthy, that's what the company is optimized for. And I really urge people to think this way, or at least trick yourself into thinking this way. There are two benefits to this thinking. One is your mental sanity. Because if you always think like you could do it better, you could solve the problem better with a bunch of smart friends who know how to do things, that is always going to be the case. And if you think you could do better and you want to do better, you'll be disappointed most of the time. And that's a path to unhappy life. So if only for mental sanity, embrace this philosophy that I would like to build software in a way that makes it possible for my team to grow, to hire people who are less experienced so that they could still maintain the pace of shipping features. And the other good reason is by thinking this way, you become more fit for the modern day industry. So if you're secretly a billionaire and you can afford to do whatever, you probably can skip this content, really. You can do other things. I mean, it's still going to be helpful if you're curious about the domain, but chances are you have other things to do. But most of us still need to be part of the industry, still need to have jobs and still need to be happy on them. And it's a good mental trick, it's a good mind trick to assume that part of your job, part of what you're paid for, is not just shipping software, but shipping software that is built such that other people can keep improving it. If you want to disagree, there are many places. One of them is these meetups, unofficial gatherings. But so far, I'm gonna stick with this. So that's why, in order to accomplish this goal, we have standard boxes, right? When I used to record like more educational, more interview prep videos, I would always start by saying, which standard boxes do you guys know? Let's walk through them. What are the differences? And everybody these days knows about application servers, databases, load balancers, caches, message buses and brokers, and other components that I should not go to. We could literally do an episode on each of them, like an hour long at least. These are useful components. It's good to reason about them effectively, but this episode is not about that, although I do want to rant about message buses and message brokers. That's a commonly misunderstood topic. So a lot of people think that there's like RabbitMQ, there's Kafka, which one is which, and I sincerely want to make a strong argument. I want to make a strong statement here that what's the difference between a message bus and a message broker is the 21st century alternative to the question of what's the difference between a class, an abstract class, and an interface. Like there was a joke when I was growing up, like 20 years ago, that a standard interview question that nobody knows how to answer is, oh, so what did you tell me? How is an abstract class different from an interface? And the short answer is just, you don't answer the question. You just need to hint the interviewer that you understand these terms and you have to condescend them, move on, like transcend and like ignore it. Let's move on. So same here with, you could define what a message bus is, what a message broker is, but in reality, this would not take you too far. The answer that takes you far is to indicate that you understand the differences in practice, but in every single real life problem, there's going to be some mixture of those required. And there are standard tools like Kafka, which you could use in different capacities. And let's talk about that instead, forget terminology. So I really want to go on record saying, please do not waste time on these arguments. Please, that's a waste of time, really. Understand them better and you'll do fine. Now, we had the set of boxes chosen. I've outlined them in the previous slide. We could argue whether this set of boxes makes sense. I would argue some of them do not make sense. I would argue a better foundation to stand on could be better for the industry. But we have what we have. And from the way we draw the boundaries between those boxes, like between the application server and the database, between the cache and a database, between the message bus and broker, for God's sake, from how we break software, distributed software, into boxes, we inevitably arrive at problems that are now standard problems. You could argue some of these problems, most of them actually, arise from the need to run software at scale, like on multiple machines, multiple nodes. I would not disagree. But again, just in my mind, a lot of problems we have to deal with are not fundamental to the nature of software being distributed. But it's mostly the function of the fact that we taught ourselves to think in certain boxes. So once we realize that the box between it, let's say the logic of the application server can partially be in the database, and it's actually a better job, or like your message broker or your message bus that solves the problem of decoupling writers from readers, so that there's no back pressure issue. Once you can convince yourself these boxes can be combined and the lines can be drawn differently, it's easier to solve some problems. And in a way, part of my job here is to make you expand your mind, so that you can redraw those boundaries in your head and then talk in standard components. So the standard problems that arise mostly have to do with consistency. When I say consistency, I broadly mean having to spend more time, more developer time first of all, and then more compute time to solve problems that have to do with parts of the system not agreeing with each other. That's pretty much it. If you have a database that is distributed and different application servers talk to different parts of the database, same data center, different racks, or different locations, different continents, you will always have inconsistencies. And that's pretty much, in my worldview, it's like 80% of what we solve in SysDesign. A good SysDesign solution avoids these problems effectively. That's my, I wouldn't say definition, but that's close to it. So once we start to deal with the consistency issues, the realm of standard solutions to these problems is sort of clear as well. We have what is called two-phase commits. Common question in interviews. How do you maintain two different databases in sync? Well, you don't just run two transactions, hoping that both succeed. You do some prepare work first in both databases, and then you have some component that pretends to atomically make both databases commit these two transactions. So that, well, both as in two databases, could be like 3, 4, whatever. So like in a way, it's an orchestrator. In a way, that's a component that is responsible for keeping the thing sane, or at least reducing the attack surface for insanity. And then, of course, all the questions, hey, what if you like start two transactions, commit one of them, the other one fails because the computer died? How do you keep that stuff consistent? That's the hard problem, in a way. Two-phase commits is a standard solution. You have this idea of conversational transactions where there is some logic, often distributed, that has to do with, things went wrong before, and I need to correct the state of the data across different nodes and locations and whatnot, so that it's consistent as seen by the user. SAGA, I used to think it's an acronym. It's not. It's literally like a literary genre. So SAGA is just when you write your software as if it has like multiple chapters, and you execute chapters one by one. And then at a certain point, you say, hey, this chapter didn't go through. We need to go back and rewrite our novel. That's how people think about designing data flows. And there are standard techniques to deal with them. I'll cover them in more details, just some teaser here. Now, first important part of the talk, of the episode. There does exist such a thing as too much consistency. And I'm not kidding. That's what you learn when you're like senior enough. When you just naturally grow in your career, you would think, that's an inconsistency. If only I could build a better framework, if only I could design it better, there would be no room for inconsistency. I'm going to claim that in most real-life problems, this thinking has a limit. So beyond a certain level, it's just not feasible to think of more consistency. In fact, I believe that at a certain seniority level, it just becomes part of the job description. Like if you're trying to be too consistent, chances are you're doing something wrong. There's a healthy and unhealthy amount of consistency. A good example that I can come with is airlines tickets booking. Like when you book a flight, you would think that it should be part of functional requirements of the system you're designing, that it's not the case when the same seat is sold to two people at the same time. So if it's like an interview question, or if you and I are working on this design on the whiteboard, both of us should ask each other and ourselves, so what if Alice wants to fly from New York to Boston and she's booking this seat number in the same flight, and then Bob does the same, and then somehow, how do you make sure it's not the case that they book the same seat? Well, you could design a system that makes it totally impossible, But in practice, and I mean, I would love to live in the world where it's impossible. But in practice, it happens. And as a company that is hiring engineers to build software for this, you have to have a healthy boundary that I don't want this to never ever happen. I want it to not happen too often. And a well-designed system that is just good enough would actually make it happen not too often. I mean, I would argue that the healthy error rate, to put it this way, the healthy inconsistency rate, if it's once in a million, you're in a good shape. Like really, if it's once in 1,000, your customer support is going to be overwhelmed. If it's once in a million or even once in 100,000, that's okay. Just bump this person to first class, and it's still cheaper for you as a company compared to hiring more engineers to build a better system. Even if it's better, it's going to be harder to maintain and it's going to be more buggy. So it makes sense to keep it inconsistent. The example Martin Kleppmann uses in his book, Designing Data-Intensive Applications. I like it. No, actually, wait, I take it back. It's from his talk. It's not in the book. So I like, but I like the example. The example is, imagine you're Amazon and you have some rare item, like the vase or whatnot, and you have like one left, and two customers are trying to buy it, and somehow your system made a mistake, and this vase ended up being paid for by two different people at the same time. So clearly one of them will not receive the vase. You have just one left. So it's an issue. But at the same time, there's a non-zero chance that even one customer cannot get it because the person who was carrying it in the warehouse just dropped it. That happens. That's normal. So Amazon as a company has a process to tell you, sorry, you ordered it, you paid for it, but we cannot deliver it. Here's your money back. Here's a gift card. Again, sorry, we did our best. We failed. So that given you already have this process in place, it literally is okay that at a non-zero rate, so you have to use this process because of a software failure. That's normal and healthy. Building stuff that is too consistent, too reliable, is just too expensive in the long run. Not making many sense, not making much sense. And I like this argument. It's a good one. So now that we have standard boxes and standard problems, we also have decent terminology to talk about what could be done better. So a lot of people today, they understand all the terms on this screen, on this slide. So I guess consistency, again, it's a big topic. Each bullet point deserves multi-hour conversations, but I just want to make sure we have the same structure in our heads. So people these days understand what ACID and BASE stands for. ACID is standard database management systems, like what we often refer to as SQL databases, even though everything is SQL and everything is NoSQL these days. So I guess ACID is a better term. ACID stands for atomicity, consistency, isolation, durability, I believe. And the counterpart to ACID is BASE. That's what NoSQL has to do with. It's mostly like key value stores with no cross-key guarantees. Like key value stores designed for the usage patterns where cross-key guarantees are far more expensive and far less reliable. They're convergent, yes, but the terms are well known. So you can use them and expect people to understand them. There's a CAP theorem. We all understand what it stands for. It's hardly applicable in the real life. It's tricky, but it exists. The term idempotency is thankfully well known. It was not the case 5 years ago. CRDTs are the new cool kid on the block. Conflict resolving data types. It's the data structure where I have a slide on that, so we'll get that. We'll get there soon. People talk about vector clocks these days. I have a slide on that too. Actually, I have slides on pretty much all of this, so we can just skip the top part. The product part is, again, we are at a certain point, which we can argue if it's good or bad, but we are at a point where certain products, certain building blocks in practice, not in theory, can be just leveraged, and people speak in these terms. So we have key value stores, we have databases. For consensus, we have existing technologies such as Zookeeper, Console, etcd. For the message bus, it's not a broker. Kafka is widely used, and we have Cadence and Temporal as Cooper Cadence, and then Temporal as a standalone product, which I believe is the right direction to evolve the industry towards. That's where I have a chat message. Conflict-free replicated data types. If I said wrong, if I said it wrong, I apologize. Yes. I actually, that it's on the slide too in the future. I actually used to call them, no wait, there are 3 different ways to call it. Conflict-free replicated, yeah. And I guess I did say conflict resolving, which is what I think they are, which is like semi-true but false. So yeah, thank you. Conflict-free. Anyways, moving forward, once we have the standard blocks included databases and caches for a long time. The standard blocks now include consensus engines such as Zookeeper, Console, etcd. The building blocks since recently include message buses and brokers, and like Kafka has earned its place, of course. And I believe the future is in workflow orchestration. What I'm talking about is beyond that, but at least we need to know about techniques for workflow orchestration, which is Uber Cadence and Temporal as a standalone product. I don't think we have time to talk about them yet, but if this episode frames us for the conversation, that would be awesome. Now, if you want to design a system that is like properly designed, and you don't know how to start, that's a common thing I hear from people. Hey, I have this blank sheet of paper, paralysis. I have no idea what to do first. Over time, I've coined two mantras, 2 tricks to unstuck yourself. One is that if you don't know what to do, if you don't know how to start, imagine you need to build the system that is not changing its state, so it's immutable. More often than not, you would build something that is not perfect for the large-scale solution, but most problems, most systems these days, they are read-heavy. There's a concept of read-write skew. Most systems would have a lot more than one read per write. It would literally be like 20 to 1, 100 to 1. You read messages in your messenger far more often than you write them, right? When you like go book a flight or book an airline concert, or book a flight or book a concert show ticket, per one time you actually book it, you check out a few. Even if you want to book it tonight, you probably open the app or the browser a couple times. So it's only normal to design systems under the assumption that there's a heavy fraction of requests that are read only. So if you don't know what to do, start thinking of this read path. Like imagine there is some magic wand, magic bullet to actually make it mutate the data correctly somehow later. But for now, focus on the part where the data is never changed, but you need to serve a lot of reads. So your read throughput should be huge, your read latency should be low, but the data never changes. That's a good trick. That's a good trick to think about approaching the problem when you're stuck. And the other trick that I also like is imagine all your data somehow fits just one singular RDBMS as a SQL database. Transactional data store that makes sure all transactions are serialized, as in they run in a strict order. Nothing conflicts with one another. It's just a strictly ordered set of transactions. Again, it's not the case for most systems. There do exist a couple solutions, most notably Google Spanner, that offer this guarantee. It would be financial suicide to build like Ticketmaster or American Airlines based on top of Google Spanner, but it's possible. But in terms of a thought experiment of how to think of this, assume you can afford to feed all your data in a single relational database management system. This would involve things that I totally do not endorse, like in the long run, such as using stored procedures for mutations. If you want to like check your balance, and then only if the balance is sufficient perform the operation, you cannot possibly make it 2 transactions because there is no guarantee that by the time the second transaction begins, the result of the check in the first transaction is still applicable. The data may have changed between these two. So whatever has to do with a mutation has to be an atomic transaction, a single transaction. But again, it's an awesome way of thinking. I'm not saying it's a perfect way of thinking, but it's a really good way to reason about consistency. So then, once you are there, we can quickly see that. So imagine we have the design that is either immutable, read-only, or assumes that there's only a single database, single transactional database being used. Once we start extending this to a proper solution, there will be effectively 2 classes of problems. Like I really thought hard about this, and I can only see these 2. One is how to not get into an inconsistent state. So that once you have a system that is super read heavy, super read throughput friendly, if it's changing the data, if some magic bullet is being designed, some magic wand changes the data, how to make sure it does not change the data in an inconsistent way. And the other one is how to not serve stale data, how to make sure the caches are up to date. These are A and B, 1 and 2. For the first one, well, that's a standard SysDesign problem. We'll get there soon. For the second one, cache invalidation is notably one of the most important problems in system design. So yes, I assume all of us are familiar with that. There is a third mantra that is another mind trick that is also super helpful. It's far more difficult to implement, but as a mind trick, it still works. And this mantra is, imagine all your requests are stamped with a monotonically increasing sequence ID. So you don't just get requests. You don't just get like JSON payloads or gRPC calls. You get command, the payload, with some index, 1, 2, 3, 4, etc. Ideally, imagine there are no skips. So you know for a fact that after 1 is going to be 2. This is actually a huge oversimplification because designing a system that would stamp these IDs is incredibly difficult. It's identical to one of the most difficult problems in SysDesign. Once you if you can solve it this way efficiently, you can do a lot of things easier. I would postulate that most real-life products do not solve this problem as fundamentally as I just suggested. They would contain internally some weak form of this guarantee, but not a strong one. But again, as a mind trick to reason about consistency, if you don't know what to do, assume this, build on top of that, and then talk about how much of this guarantee do you truly need. Maybe you can use not a single sequence ID space, but multiple spaces. We get to vector clocks, right? We get to logical clocks. That's easier. We can use partitions, stuff like that. So yeah, this sequence ID stamping is also known as total order broadcast. Martin Klapman covers this topic a lot in the book, not in the talks, although in the talks too. That's why I recommend the book a lot. And yes, I personally believe it's one of the biggest mistakes the industry has made, that we talk about literal actions as the fundamental building block. I think if we could instead talk about total order broadcast as the foundational component, and then derive literal actions from there, our engineering will be better on this planet. But well, we are where we are. So yeah, I covered this. Most real-life solutions do not have total order broadcast internally, although I would argue major ones like AWS or Google Cloud, they have multiples. They effectively have multiple implementations of total order broadcast inside themselves, much like the old joke goes that every large enough piece of software contains a poorly implemented Lisp interpreter at least once. I think it's true. So now, for the next part of the talk, probably the most interesting one, I'll cover several concepts of SysDesign, if only to refer to them later on as more isolated topics. These topics always result in tons of questions, so that's probably a good time to interrupt me, anytime. I'm recording my screen, so if you want to talk to me, just ask away. No need to chat. And to be super clear, these are not bleeding edge concepts. They're not something that we have devised a couple of years back. Most of them date back dozens of years. But thankfully, and I like it, as we speak in 2024, all of them are being promoted from some sacred knowledge to everything, to the stuff we are supposed to know at a senior enough level. So there's a lot of value in understanding them. With this being said, let's go. Number 1 of many. Everybody knows that you have strong and eventual consistency. What I want to focus on is that eventual can and does mean a lot of things. A common mistake I hear is that people think that, so there's an object, right? It's of certain version, and then it can be like moving forward. So then its version improved. Its version is upgraded, like version 1, version 2, version 3. And then if you issue a GET request to a database, to an application, to its replica, you get some version back. Maybe you get version 1 and then version 2. And then as you keep making these requests, eventually, as the name suggests, you will be converging towards the latest version unless it's changing frequently, like super fast. That sounds right, but it's not true. Eventually consistent just means eventually you will have some probability of getting the correct result. You can make a GET request for like your imagine I make a transfer. Imagine I send you money from my bank account, and then I make a GET request and I see that the money was subtracted from my bank account over the same connection to the same node, hypothetically. Eventually consistent implies that I can make the same request again and suddenly get an older version of my balance. That's not a mistake. That's not an error. That's allowed if the system is eventually consistent. Or it can go back and then again forward. Or it can even return incorrect data. Like maybe I'm making the transfer to you, but I'm not supposed to be able to do it because I'm out of balance. But somehow when you refresh on your balance, hypothetically, for a moment you can see increased balance, and then it goes back to what it was because the transfer from me did not go through. That is not incorrect. That is acceptable by terms of eventual consistency. Eventual consistency is an extremely broad term that is literally is the indulgence for all sorts of mistakes. What most people refer to when it comes to eventual consistency is two things. One is the version of the data you get if you talk to the same node. If you reconnect to a different node, everything breaks loose. But if you have a single connection open to, let's say, an application server or database node, you expect that once you perform GET requests, you would always get the data that is moving forward in time. That's the assumption most people make. It's mostly true, although not entirely. And the other assumption is called read your own writes. I'll have a slide on this later. So when you made the change and you get back and you request the result of what you just changed, you can expect the mutation you just made to be applied. Again, not always true, but mostly true. The TLDR of this slide is that eventual consistency is a far looser term compared to what many people can assume it is. There is a dedicated term that I want to focus on that is called strongly consistent reads. So like in practice, in most systems, the read path and the write path are separated. So if you change the data, you go, like your request goes one way. If you just need to read the data, it can hit a replica, a cache, or whatnot. So like by design, reads cannot be guaranteed to be up to date because there's no guarantee that, well, imagine the system is a single box. So it serves everything sequentially, hypothetically. By the time the response to your read request gets to you, the data may have already been changed. So if you make a read request call and you get back the result, you cannot assume this result is up to date. It can already be outdated. So if you need this assumption to be correct, if your logic depends on that, there is a concept of strongly consistent reads. There's a concept of a read that has to follow the right path. So it's more guaranteed to be consistent. The best way to understand this is to assume that eventually consistent reads can hit the replicas and they do not mutate the system. But strongly consistent reads, they have some counter per each object that is being get, and this counter must be incremented per every strongly consistent read. And this increment of the counter should also be unique per read. So you have to be very careful with consistently updating this counter. That's the path, the query path that would be taken by a strongly consistent read. You can go all in with idempotency and say, I want to like always be able to get the balance of, let's say, Alice's account at this timestamp or at this version. In which case, I need the system to guarantee that once I get the response, it's always going to be the same. Identical response to identical request. Most systems are not designed like this, but logically speaking, that's where you would get to strong consistency. And have a slide on this. So I hope this one was good enough. Idempotency. We don't have too much time to get into the details. I have this blog post that talks about the way to get from idempotency to strong unimpotency, where the guarantee is actually held. Basically, what most people know about idempotency is that if you want some mutation to never be applied more than once, what you can do is send a token with a request. And the logic of the request is apply this mutation unless you have already applied the same mutation with the same token. That sounds like a clever technique to deduplicate stuff. And presumably, even if your request is received by multiple nodes of the system, they somehow coordinate between themselves so that the same idempotency token results in at most once mutation application. Good stuff, cool stuff. The real life application is, I see it all the time myself, And when I talk about it to people, they confirm they see it too. When you post a comment on Facebook from poor internet, like when the plane is about to be taken off, sometimes I just type it in, I press send, and nothing happens because I'm like flaky in my connection. And then when I land and I open Facebook, my comment is posted 10 times or 20 times. That is certainly because whoever built that backend API at Facebook does not use idempotency properly. Maybe because like the mobile internet connection hits a different node and different load balancer hits a different Facebook node and they don't coordinate. I don't know, but that's wrong. That's not how idempotency is supposed to work, and that's exactly what idempotency is supposed to solve. Now we have order. Oh, this is getting interesting. This is getting cool. So we have this idea of let me take a step back. So sequentially ordered stuff, if you can stamp sequence ID, and if it's like 1, 2, 3, no gaps, that is almost by definition what is called total order. Total order means that for every 2 events, you know for a fact which one came before the other one. As I said before, total order broadcast is a difficult problem. If you can afford to build your system so that everything is totally ordered, if it's not too expensive for you, by all means I recommend that because it makes designing software so much easier. But you have to understand that total order is often not only hard, but impossible. And my favorite example here, impossible as in imposes too many constraints that may be against your functional requirements. So you can do it, but it's going to be too slow and too expensive. And my favorite example here is going from Newtonian gravity to Einsteinian relativistic gravity. Because if your system is deployed on satellites that roam the solar system, then at a certain time of year, so to speak, latency between different nodes can vary greatly. Like on Earth, you know that Europe is closer to like New York and further from Australia, but Japan could be closer to Australia than to New York. But imagine your system is deployed in servers where the continents keep drifting, and then today somehow these 2 nodes are close to one another, and then a month later they are the furthest away nodes in the system, and the other ones are closer. So if you want total order, if you want proper consistency, every single request would have to make sure that its position in this queue is placed properly, agreed upon by every single node in the system, or at least the majority, or at least the leader, which can be far away from you. So if latency is important, that's my message. If latency is important and throughput is important, demanding total order is a bit too expensive all the time. And in practice, total order is just unneeded. Like for instance, if you have Google Docs, chances are, if the doc is shared within your own organization and nobody else can see it, you don't like. If you and I work on the document together on the same paragraph in the same sentence, it's sort of important who pressed backspace first. If these 2 documents are different, nobody cares. If one of them is from a company in Europe and the other one is from a company in Australia, they can be in different places, and the company, in this case Google, that maintains Google Docs, does not need to be able to answer the question who was first. You pressing backspace in Australia or me pressing paste in New York. So that's an example of where the total order is unnecessarily expensive and not needed. And that's what partial order means. Partial order means sometimes, for certain events, what came before can be established. But on average, for the most part, not only it's not necessary, it's impossible to tell which came first. I really do not like it when people say, oh, partial order means I have like replicas, I have partitions. But in a way, it is what it is. If you have partitions, like Kafka partitions, database partitions, technically speaking, this is partial order. Because like within one Kafka partition, you know for a fact in which order certain 2 events came in. You know which one came before the other one. In a multi-partition Kafka topic, that is by definition possible to tell. That's why choosing the right partition key is super important. And of course, as engineers, we understand that it's the price to pay. Contention is the price to pay. If you partition correctly, what never conflicts with one another is in different partitions, and you're fine. But then what has to be totally ordered is totally ordered within this partition. If you partition incorrectly, you create contention and expensive operations where they should not belong. That's true SysDesign. I shouldn't really talk about this for too long because I could go for hours. So yeah, what I want to say at the end of this slide is that at least two products that are widely used do guarantee total order. And it's Google Spanner with what is called external consistency. They have highly precise atomic clocks synchronized by satellites across data centers, specifically so that, like, I mean, really no kidding. There are open source projects right now that try to mimic Spanner's guarantees, but the way Spanner works is they have synchronized clocks physically down to like nanoseconds. And I think each transaction there takes at least 7 milliseconds by design, so that it is guaranteed to be replicated to every single other data center, which is like each mutation. The reads can be, of course, eventually consistent, as covered before. But like realistically, that's super expensive. In addition to Spanner, the other product that is by design totally ordered is Redis. But as you can imagine, it's quite easy to be totally ordered in a single machine. If it's single-threaded, you're totally ordered. If it's mutex locked or if it's lock-free queue, it's totally ordered. Now, so yeah, the message here is that if it's totally ordered within a single machine, not too hard. Totally ordered in a distributed setting where you can lose machines or connectivity and still be correct, expensive, painful, hard. Don't do it yourself. Use some product. Use some existing technique. Or at least isolate this part so that only a few people in the company have to work on this while the product can still be developed further. The next topic is transaction isolation level in databases. So again, it's close, but not entirely the same. Back from, I believe, the 70s, we have this idea that the strictest transaction isolation level is serializable. Serializable means total order. There's a bit of confusion in terms, because serialization can also mean like parsing data from binary format to whatnot, or like from JSONs and back to JSONs. I like to call the latter marshalling, whereas serialization is in lower level world. Serialization is reserved for ordering. So serialized transaction execution is effectively totally ordered transaction execution. And yes, most databases, I know for a fact for Postgre and MySQL, of course, they do offer this as the option. You can configure your database to be serializable. It may be called strict serializable, I forgot. I think it's serializable in Postgre, and I have no idea about MySQL. Note that even Postgre is not by default serializable because it's too expensive. So yeah, I shouldn't talk about this. We covered this in tons of details. Of course, Redis is serializable because, see above, it's single-threaded by design. Other levels of isolation are leaky, and TLDR is welcome to hell. There's just, like, in fact, that's one thing I do not agree entirely with Kleppmann on. I think he spent too much time talking about this in the book, like, academically speaking. I do not believe many engineers should know this. I think, thankfully, we're moving towards the world where things just work. Only a handful of people, most notably DBAs and the storage stream guys, have to understand this in detail. But yeah, when I first read about this, I was shocked. I was terrified. So you have this concept of select for update, which if you forget to do it, then your code would most often work until it doesn't, and it's a non-trivial to find error. And most companies apparently have these errors. I don't like it, but that's how the industry evolved. Let's not blame them. Let's just offer better solutions. So yeah, if you have to be, like, unless you really like this, unless you really like databases, like SQL databases, if you have to be thinking of select for updates, I recommend changing teams or companies, seriously. That's just, it's going to be a hellhole. Like, either you really love this and want to educate other people and improve these things in process, or you may not be doing the 21st century stuff. The next topic I'd like to extend to is taking the idea, it's all connected, right? But certain things grow from one another. I'd like to extend the idea of total partial order and causality into this and idempotency into this idea of read your own rights. So again, if you have a connection open to the database here is an umbrella term. It could be some component that acts as a database. It could be your application server that exposes the API that logically has stuff such as get put, like post, read, write. So then you become the database, source of truth for some data for another service. So eventual consistency could be super tricky. We talked about that. strong consistency could be super expensive. One compromise that is often used in the real world, at least it's a term to be aware of, because many interviewers know that. This level of guarantee is called read your own rights. Read your own rights stands for, if I've changed something and you have confirmed that this change has gone through, next time I read that, please return me the data with this change applied. As simple as that. Well, again, academically speaking, that is not a correct explanation. You can certainly do better, and like you can formalize the guarantees. But people understand this. People use this term, and all of us are better off using this too, especially with people who are more pragmatic and less academic. That's a good skill to acquire, to change languages and terminologies based on the audience. This is one of my favorite slides. Again, could be like an hour-long episode, but fundamentally, it connects to so many other dots, including not covered in this talk, such as like Haskell, purity, side effects, functional programming. But the idea is that if you build your code in a way that is deterministically executed, if there is no room for ambiguity, if the code is guaranteed to give you the same result no matter what, if you can satisfy this guarantee, you can do a lot of cool things, knowing full well you'll be fine in the long run. So, for example, if a database has to apply some transaction, an expensive non-trivial transaction, if the transaction language, if the way you express the transaction is designed so that it guarantees deterministic execution, then the database replica could just receive the transaction from the leader database, right, and apply it itself, knowing that the result in database contents will be the same on the leader and on the follower. So once you can afford the guarantee of determinism, what is called pure functions, once you can afford pure functions with no side effects, you can build your systems in a replayable manner. So maybe you can take some older snapshot if your machine died, takes a snapshot from 10 minutes ago, an hour ago, and just applies the mutations that took place after this snapshot. It is guaranteed to arrive at the same result as the other nodes, and you can leverage this. If we do it like all the way, if we go all in on this topic, we get to event sourcing, where the source of truth of the state is not just the database contents, but the contents of the stream of mutations. You have a totally ordered stream of mutations, and you know that offset in this stream uniquely defines the state of the data. But so then every database becomes a cache, because the source of truth is not the database contents. It's the stream of mutations plus the offset, single number. That's the perfect-ish world that is sometimes desirable, mostly not, separate conversation. But I do want to cover what you need to do if you really want to be deterministic. Well, first thing you do is you replace randomness by pseudo-randomness, because if you use random numbers, sorry, you cannot be deterministic by design. But it's a lot more than this. Then you cannot use anything machine-specific. So like IP address, no. Machine name, no. Operating system, no. Like use floating point, use some standard compliant floating point. Or in fact, please use integers. And please do not rely on overflows. They're often non-standard. You'll be surprised, but I think even in standard C and C++, unsigned integers must wrap around if you like overflow or underflow. But with signed integers, there's no guarantee by the standard. It's perfectly legal for your binary. If you do like 1 billion plus 3 billion in a signed in 32, the result is not guaranteed to be what you think it should be. So got to be careful with that. Another awesome example I use is hash map traversal order. So like sorting should be every single sort should be stable sort. Unstable stable sort means when the elements are equal, you do not change their relative order. In unstable sort, if the elements are equal, if the sort key is equal, the order could change, and that suddenly becomes non-deterministic. If you use a hash map, if you have some traversal, some container, hash maps are inherently random because it's a hash. And if different nodes, I mean, you can use different hashes. That's the whole point, right? You can use different hashes for different performance characteristics on different machines. So this machine has more RAM and slower CPU. So there's a different hash function because this architecture is designed to compute some hash faster. surprise, it works perfectly fine if everything you do with hash maps is get set, like check if the element is there. If you want to iterate over elements in a hash map, the order is suddenly different. And an operation as innocent as take the first 3 elements is unpredictably bad. So basically, if you need to have a hash map, keep in mind it has to be your own manually implemented deterministic hash map. And of course, everything that has to do with time is incredibly painful, because whatever time is not reproducible. Like you get current time, you sleep for 1 second, or you just make a request somewhere, you expect it to take however many like nanoseconds. Suddenly the result on different machines is different, and the order of execution is also different. So when you start coding for determinism, all of these have to be carefully dealt with. One of the starting points of Temporal, I'm not sure if Cadence did it. Sorry, I'm not sure if Cadence did it. Temporal certainly does. One of the setting points of Temporal is that you can run a workflow with a long plane, like long lasting sleep. Like if you need like the user to, I don't know, pay up or be downgraded to a free plan after a month, your workflow code could literally read, send welcome email, wait for like sleep 30 days. If the user is not yet a paying customer, do that. But that's a very special case. And such a workflow can only be executed reliably by a system such as Temporal, specifically because everything else has to be guaranteed by the developer to be deterministic. So the sleep can be introduced, but in a clever way handled by the orchestration framework. I wanted to insert a plug here that Postgre is quite famous specifically for making sure the binary contents of the database, like of the B-tree nodes of individual most granular level of data storage of the database on disk, is identical in Postgres across replicas. It has pros and cons. I mean, the pros are awesome because everything is reproducible and like pluginable. Like you can take the snapshot from one machine, insert to the other one, you're fine. But the con is that, for example, growing the database is nearly impossible. You cannot just say I'm going to replicate it from one node to the other where the other one is bigger. Like it cannot do it. It can only do it literally like binary bit by bit copy. That's by design. It's a blessing and a curse. So all I'm trying to say is that deterministic solutions exist for a long time and they have their place. And I'm not saying binary identical data is the future, but I do believe strongly that if you can make your coding guideline, your DSL if you want, if you can make it deterministically reproducible, oftentimes doing it early on saves a lot of time moving forward. And I recommend that. Is it correct? Conflict-free replicated data types? Thanks. Yeah, see, even the first line of the slide says, I often encode them incorrectly. Yeah, so CRDTs it's a relatively new concept. People often even don't know what it is, although I think it's at least 5, 6, 7 years old in practice, and in theory, of course, far older. It's the idea that if a certain data structure, if a certain object can be designed, like data schema-wise, such that it's not important in which order you apply the mutations, then it can act as this magic component where partial orders become total order. It's one of those rare cases where you don't care about the order, so that you can receive requests in any order, because eventually, and quite soon, your final state is going to be correct. My favorite example here is the counter. Like imagine you have you're big on Twitter, and you have Lady Gaga, who has millions of followers, and there's a like counter on her post. Hypothetically, imagine you want to make it precise, because why not? Like clearly, if she posts something and people start liking it, it's a huge point of contention. If every single like results in being a message published to the same queue, where the messages, this like increments have to be processed sequentially, it's just not going to be effective. It's going to be tons of contention. Like, why would you want to wait until your like is counted in line of millions of other likes? But the like counter, just a number, has this amazing property that you can just aggregate it, right? So different nodes can just say I have counter on my own node, and then like once a second, once a minute, I don't care how often, it just synchronizes, like batch add to other like to the global like counter. this data structure, it sounds like a trivial example, and it is, but this trick immediately lets you, like, takes you off the hook with contention, because the data type for ads offers this simplicity of aggregatability without needing to know the order. So, I mean, the idea of incrementing counters is just a trivial example. There are more examples. For example, you could have this insert-only set. If you have a set where you can insert elements and remove them, then reordering operations could affect the end state, right? Because you don't know if you removed after the insert or before. But if you can only insert, it's still a CRDT. You can batch it, and it's all good. And the counters, of course, could be hierarchical. Like, it's not just a single counter. You could say that it's a hierarchy. It's a tree of counters, and each node can also be its own tree of counters. It still is a CRDT. And if, like, when I said counter can only go up, you can also make it go down. That's not impossible. If you need it to never go negative, such as a balance, then it's tricky. But the counter can go up and down, no big deal. And yeah, the first obvious example of something that cannot possibly be a CRDT is the counter that cannot go negative. So if there's a balance, whenever you have a point of contention, my favorite example is if Alice wants to send Bob $50 and Charlie $50, but her balance is 75. Clearly, like, if it's a requirement of your system that you can never go negative, keep in mind, we talked about this before, not all systems must be consistent. In fact, banking systems in the modern world often are inconsistent, partially by design. But hypothetically, if we want to maintain a guarantee that the balance cannot go negative, you sort of have to, at a certain point, have these two withdrawals from Alice to Bob and Charlie respectively. You need to have the order to them, because the first one will succeed, the second one will fail, unless you get more clever with, like, batches and stuff. So that's not a CRDT. Or more real life examples would be, if you block someone, you should not get messages from them in a messenger. So clearly the order is important. Another big topic, I don't think I should go into all the details, but the idea is that people talk a lot about at least once, at most once, exactly once. Again, part of me is converging over the past couple of years that it's a false dichotomy. So again, the correct answer is not to give the answer, but to explain that you understand these things and transcend them. But fundamentally, the idea is pretty simple. If something is at most once, doing it more than once is against the functional requirements. If it's at least once, not doing it would be against the functional requirements. Exactly once has to happen exactly once, and that's it. I know it's a trivial phrasing, but here's the trick. You can only do exactly once if you control the entire system. You need to have every single step under control. Every single component must totally respect all these idempotency guarantees. Because if it does not, you just cannot guarantee exactly once. Like, try sending an email exactly once. Maybe everything in your system is exactly once, but ultimately you're going to send a message to an email address via the SNTP protocol, which you just send it, and then the machine that received the request dies. You have no idea if the email was sent or not, and there's no way you can check it. Like, you can wait until the user receives it and ask if they did, but it's not going to work. So you have to send it again. You have to send it again, knowing that under the assumption the receiving API, the API you call to send the email, cannot give you a 100% guarantee that it respects idempotency correctly. Sometimes you will do not exactly once. You can resend it, which would be at least once, potentially more than once. You can not resend it, could be at most once. Some are lost. We talked about this before. It's actually okay to be inconsistent. Just keep in mind that unless you can guarantee that every single piece of the system respects exactly once, your entire system will not be exactly once. People keep forgetting that by the HTTP standard. So actually two things, if you want to go down. One is standard timeout for TCP IP is, I think, 90-something hours. So like it hardly happens in practice, but it's not against the contracts of modern day internet that you send a packet to Australia and then a day later they receive it. That, like, it may happen. There's no guarantee. We do not live in the world where operating systems and network hardware has strict upper bounds on time. Clapham talks about this too more academically. What is more, I don't expect any of us to hit the case where TCP packets take days in transit, but what we may expect is that by design, HTTP GET requests are meant to be non-mutating, idempotent. So when your API exposes a GET endpoint, by the standard you have to commit to the fact that multiple GETs would not make your system incorrect. That's why there is not only GET. So basically GETs and I think heads and methods and whatnot, your system should handle them in this idempotent setup so that having the same request hit you more than once should not affect the system. If you want something mutating, that's what put and post are for. I mean, pragmatically speaking, that means that load balancers and like Nginx and HA proxy technically are allowed to resend the GET request to you. There's no standard compliance rule that once you send it out, you never send it out again. It can be retried. Even if you say no retries, it can happen outside of your control it can happen on the level of AWS load balancer, literally. I'm not saying it does. I do not think they do it, but it can happen in a certain part of your data flow. So just keep in mind that GETs should not be used for exactly once operations. Yeah, what else do I have on this slide? Yeah, message ID for emails. Reading further, that's exactly what idempotency would do. A lot of times people talk about what is called fire and forget for stuff like telemetry. Like a famous example would be like website user behavioral analytics, like a heat map to draw like where do people click with their mouse and how often do they do this and that. Analytical frameworks in JavaScript almost always use the paradigm, the concept called fire and forget, which literally means send a request and forget about you having sent it, which is nowhere near the dichotomy of at least and at most once. It can be multiple times, it can be 0 times, it's perfectly acceptable. That's just keep in mind, it's not exactly at most once. It's fire and forget, but it could arrive more than once, logically speaking. And again, it's a theme of today that consistency, like there is sort of thing is too much consistency. So oftentimes the true design is best effort at most once. So please try to be, best effort exactly once. Please try to do things exactly once, but if once in a million times or once in 10 million times you do it twice, we have mechanisms in place to detect that and to correct for that. That's how systems tend to work these days. Notable exception would be Web3, like blockchain transactions, but that's not the topic for today. Getting into the weeds, the most interesting stuff. Source of truth. I've adopted the advice from my colleague who's from New York. She says that by traditional Boston English rules, it should be hyphenated. No spaces but dashes. I never liked it, but I thought he has a point. Human brain can process stuff easier if it's a single block of word, no spaces. So since then I'm writing source of truth as one word. So source of truth is the concept that if uncertain, if you don't know what the ground truth is, it's there in a particular place. Now, it's important to understand that source of truth can be logical or physical. And it's oftentimes, it cannot be both. It's either or. If you need to abide by the CAP theorem, if you need it to be distributed so that if at least you need to ensure that your system can lose machines, they just die and fail, and not lose data, if that's the case, you cannot have physical source of truth. Because, well, any machine can die, right? So if the data is source of truth there, and that machine is gone, how do you know what the truth is? So most often, what you end up doing is you have a logical source of truth. So there's no physical location of data, like in memory, on disk, on tape, or whatnot. But you have the guarantee on the API contract level that if you make certain calls in certain order, if you use certain idempotency tokens or whatnot, sequence IDs, then what you get back is the data stamped by the source of truth. And the illustrative problem here is, again, Ella sends funds to Bob. We need it to be an atomic transaction. Hypothetically, we just want to make sure nobody ever sees. So like if you get balance of Alice and Bob, they should sum to the same number. Like let's assume the functional requirement is that you have this batch get operation, balance of Alice and Bob simultaneously, and throughout any sequence of operations of Alice and Bob sending money to each other, the sum should be invariant. They should not change. Sounds naturally correct, but imagine somehow we went through an acquisition or just some legacy code, and Alice's account lives in DynamoDB and Bob's account lives in Spanner, Google and Amazon. Clearly, there's no way to run a transaction between these two in an atomic fashion. I mean, I would not be so confident. I would not be surprised if they're developing some like two-phase commits across clouds. But let's assume it's the case. If it's like Mongo and Redis, certainly you cannot do it atomically. So how do you build a system that satisfies the functional requirement that batch gets between Alice and of Alice's and Bob's balance are possible? And with respect to every single of transfers between them, the batch get returns the sum that is invariant. Well, the truth is, you cannot have a physical source of truth of Alice and Bob's balance in different databases. You could have this copy and write idea that, the company is in the process of migrating balances to like Postgres. So whenever I have to run a transfer between Alice and Bob, if one of them is not yet migrated to Postgres, I'm going to migrate them to the same database and then run a transaction. That's a good pragmatic solution. That's possible. But again, single database, single node Postgres is not sufficiently reliable. Multiple nodes Postgres, nodes can die. So the truth is, in most systems where you need consistency, like to a certain degree, like decent level of consistency, not just best effort consistency, source of truth could be like will have to be logical, not physical. It's not guaranteed by the storage of the data. It's guaranteed by the API contract of you getting this data. And this API contract can do a lot of clever things to ensure that whatever state the data inside the system is, what the user sees is consistent. For example, in the case of sending funds from Alice to Bob, you could have like epoch numbers, eras, like epoch 1, 2, 3, 4, and then the batch get operation could say, okay, get current epoch number, it's 1700, 345, and now get balances as for this epoch. This way, even though the data can be in transit for Alice and Bob, once the epoch is marked done, the result you get is consistent. That's an example, quite a simple, I think, example of a logical source of truth. Yeah, and of course, it goes without saying, right, that if you need to mutate the data, you mutate it at the source of truth, whereas reads could be distributed across read replicas and whatnot, caches. We're coming to a couple last slides. So I think I covered exactly these three in one of the first slides as the example of standard solutions to the issues of consistency. Don't quote me on this, but in my book, they are almost the same thing. It's like looking at the same concept from different angles. They are so easy to logically convert one to the other that to me it's like an NP-complete problem. If you know how to solve one, you can solve all of them, and vice versa. They are identical. Two-phase commits is the idea that you prepare the transaction in two different databases or different nodes, and then you atomically try to apply it, which is impossible, but at least the attack surface, that amount of time, the likelihood of the issue affecting you is dramatically minimized. That's the correct statement. So that it's on average, the machines don't die that often. So if you use two-phase commits, it is on average far less to correct if bad things took place. If you need to correct stuff, that's what compensated transactions are for. I think the logical difference is that two-phase commits would be like on a database level. So you make one two-phase commit, change one bit of data, and then the other one. And as you apply the second one, you sort of know for a fact the first one is fully applied in both or more than two places. Whereas for compensating transactions, it's okay to make multiple changes in a best effort setup. And then once you realize something has failed, there is some piece of logic that guarantees that the state is eventually reverted to a consistent one. So it's more work to compensate, and it's on the user to compensate. But the idea is that the author of the code has to implement all these compensations so that whatever happens in process, in transit, results in a consistent state of data. That's exactly what I do not like in modern software development. That's exactly why seemingly trivial operations in enterprise can take weeks and weeks to develop and launch, because something literally trivial suddenly affects 3 databases, and then there are 2 ongoing migrations. Source of truth is being changed from Mongo to Redis or whatnot, and to do something literally 3 lines of code, the team has to work for a long time, and then they test it on staging, under stress and whatnot. If only they could use proper DSL to guarantee this on the infrastructure level. Oh wait, it's starting to exist, but we'll get there. So yeah, 2-phase commits, database level, compensating transactions, user space, user code level, and I think to me sagas are just the way to reason about how you write your code that does compensating transactions. So like in a single machine code, we all know how to use try catch with exceptions. Saga is the way to write compensations in catch blocks, so to speak, like logically speaking. Yeah. I think it was you, Ivan, who told me that an amazing analogy to, it's a detour, but it's a good detour. So when you talk about single machine consistency, the 2 basic primitives for synchronization would be mutexes and atomic variables, atomic objects. And an amazing way to explain how they differ is that mutex is like if 2 roads cross, the mutex is the traffic light. You go there, you wait for the green light, you stop, you wait for the green light, you can go further. You can have a clever traffic light that sees you coming and makes it green, but it's still a traffic light, and you still need to slow down. The atomic variable is like a roundabout. So in theory, you can just go through. It's slightly slower, but in case of no cars, you can just breeze through with a minor slowdown. So in case of, ideally, if there's no contention, ideally, the way it's supposed to work in terms of synchronization, if there's no contention, nobody waits for anyone. If there's high contention, you need to not block anybody for too long. You need to set them in the queue. So mutexes are good for super high contention because you can cleverly orchestrate who goes next if you have priorities and whatnot. But if you just need to make sure it's synchronized with in a low contention environment, you can use atomic variables, atomic swaps and whatnot. So I think same applies here. You have this optimistic consistency where you assume nobody's going to work with the data that you're working with, and you just make all those changes and then confirm for yourself you did not break the state of the data across your transactions. And if you did break it, you compensate for it. That's what that's what Saga would look like. As opposed to 2-phase commit, where you say, I'm going to change these data in these different tables and different databases. You introduce this dreaded cross-database distributed lock-in, which I think is horrible, all the time, but people use it sometimes because legacy and it's easier to ship like this. So if you lock everything across databases, across nodes, shards, locations, and whatnot, that's effectively 2-phase commits. It's safer, but more prone to long-lasting outages because the lock has to expire if the node has died, stuff like that. Whereas if you're more optimistic, like in the roundabout case, on average you're doing okay, but if suddenly you find yourself in a high contention environment, the recovery time is longer. That's a short story. I hope it makes sense. I hope it does. Thanks. Another amazing idea is, again, I'm surprised people started talking about this recently. Literally, I did not hear this term 3-4 years ago, even though the concept of course existed. The idea is that in order to make sure the system can be consistent while applying a steady, healthy, large load of requests, the stream of requests, one trick you could do is you can decouple where the requests are coming from and where they are executed. Decouple as in separate them logically. The best way to explain it is through what is called the back pressure problem. Back pressure is if suddenly, I'm not sure what the term is in English, but if suddenly imagine the stream of requests. suddenly is of higher throughput, of more requests per second than the stream of than the capacity of whoever serves the requests. So you will inevitably result in a situation where some requests are queued up. Like there's just no way you can even the logic to drop them should be. What's that? Yeah, it's actually what my thesis is about, but it's in Russian. It's the theory of mass like serving multiple agents. There's a theory for that. That's where Poisson processes come from and stuff like that. Let's say it's a game theoretic discipline. So yeah, basically, at some point you will have a situation where the inbound stream of requests exceeds the capacity of whoever processes the requests. So you will have some logical queue somewhere. I have no idea, man. Теория массового обслуживания in Russian. We can Google that. I really don't know the correct term. So basically, if the queue can possibly emerge, even the logic to start dropping requests has to be implemented somewhere, right? Like the queue size has to be computed somewhere. And the concept, the idea, the term back pressure is about the fact that if you have a multi-stage process, the traffic jam, the large growing queue in one place will eventually penetrate backwards. So whoever sends requests to the entity that sends you requests will also end up creating the queue. And the queues are going to grow here, there, and everywhere. So that's exactly the back pressure problem. The canonical solution, of course, is that whichever entity receives requests is allowed to say, I'm full, my queue is full. I have a small queue and it's full, so come back later. There are standard responses for come back later everywhere in software engineering. There's come back later in Unix sockets, like E again. There's come back, I think in files too. There's come back later in HTTP. What's that? System of mass service. Sounds good. I guess that's it. Thank you. So to solve this back pressure problem, you need to learn how to correctly, at the right place and time, send requests back. Or you can take a step further and say, I'm going to have queues that are not part of my business logic code. My queues would be hold on. Yeah, I'll Google that later. I'm recording my screen. So the queues would be outside the business logic of the component that does the job. So it's a very, I should take a few steps back. It's a very clever idea that when you design a system, according to Conway's law, you need to make sure that the right people are building the right parts of the system. So the isolation is in order. My favorite personal example here is HTTPS, TLS. So when I first started having my own startup, I figured, I need to support HTTPS somewhere. So why don't I find some component for Node.js that does HTTPS termination to confirm the certificate is valid and whatnot? And I built that, and we used that. And then a few weeks later, I realized it was a terrible idea, because the proper way to terminate SSL is to not write code for that. It's to use either AWS, Amazon's SSL termination, where you upload the certificate to Amazon and they send you decrypted traffic, and they are the gatekeeper. If the traffic is not correctly encrypted, go away. Or you use some other components such as Surprise Nginx, or Apache, I guess, but I prefer Nginx. The wisdom here is that the business logic of my code that parses JSONs and talks to database should not be intertwined with the business logic of protocol, intricacies, details. That's a very clever idea, because then later on, if somebody needs to change the port or add more fields to JSONs, the smaller, the more self-contained the code they have to deal with, the better off we are. So certificates, distribution, SSL termination, security of who sees those certificates and where, that's a different department. That's a different part of software development. So this idea of proper boundaries can be internalized further. And if your system has a queue of the inbound queue of requests, once the logic of the queue becomes non-trivial, you probably want the queue to be built by some other team, because it's going to be configured differently by different team. Like your DevOps may want to make it slower or faster. They may want to fail more requests. Analytics, telemetry on the queue would be same logic, right? For different queues in different parts of the system. So the concept is that your code focuses on the business logic, and the queue is built by someone else and run by someone else. And the keyword here is decoupling. Whoever sends requests to you has no clue what your request drop-in strategy is. And you do not need to know, as the service owner, which queues are put in front of you. This can be changed later on. You can write the code and leave the company or be in a different department. And then in production, DevOps would decide to increase the queue size because that's what they need for this particular customer. That's normal and healthy. And that's responsibility segregation. That's the concept that, of course I should say that if you want this request to be replayable, if you want them to be persisted somewhere, the queue is often Kafka. If you can drop them, if you can afford to just time out some requests, it is probably more like RabbitMQ based solution, AMQP protocol. You can also introduce some like quality of service, which ones have higher priority, which ones are routed where, different conversations. That's dangerously close to the task queue problem at a different level. But fundamentally, the concept of decoupling is exactly this. You write your code that serves requests at the pace you can serve them. You are allowed to drop them the moment you're overloaded, and the queue in front of you does the job. I want to talk a bit more about the idea, because to me, this is one of the biggest misunderstandings of the industry. The term OOP, object-oriented programming, was originally meant to mean exactly this, that you have objects that talk to each other via messages, and each object has a small incoming queue of messages. So the fact that if you ask the modern day engineer, what do you think of OOP, they would say it's interfaces, abstract classes, public, protected, private, and encapsulation, polymorphism, inheritance, which I think is a disaster. Like, thankfully, it's coming back slowly. We no longer use these terms, and we no longer assume knowing OOP means knowing public, protected, private, because the true OOP is Yep, Erlang is part of the conversation eventually. Like, I think Erlang and surprisingly Objective-C are the longest living pure OOP programming languages these days. But it's kind of deck, because if you think about like Temporal or Cadence, that's in a way the better way to run OOP. So the rant is that proper OOP involves objects talking to each other. Objects are like singletons in the system, and you can logically extend this for objects to be distributed singletons. They can be distributed across machines so that if a machine dies, a singleton is still alive and well in a logically consistent state. And we talk about actor models these days. And to me, actors are closer to objects in the original OOP state than class instances in JVM today. And yes, if you use OOP correctly, logically in front of every single object, there's a message queue. So objects presumably process messages coming to them in a sequence. There's a partial order. Like, there's no total order, most likely, because there are multiple CPU cores. They're like thread pools to work with different objects. So there's no possible way. There's no need to argue that object A serving message 42 happened before object C serving message 71. But for each particular object, the messages are parsed and processed in a certain order, which is a partially ordered system of messages. And to me, that's a fundamental responsibility segregation concept. To me, that's where decoupling consumers and producers should stem from, which I hope talking through this set your mind straight and free compared to modern day way of explaining this. It's not going to happen today, but sometime soon I'll talk about possible ways to extend the logic of Uber Cadence and Temporal into this distributed singleton daemons that are ever living with a consistent state. Not today for sure. Trying to save time. I guess the last part here is, even though consumers and producers being decoupled is a relatively modern term, the term CQRS is quite old. And thankfully it's starting to take the meaning it was meant to take from day one. CQRS stands for Command Query Responsibility Segregation. It's exactly the idea that every single request, be it a command mutation or a query read, is like a small boxed down envelope that is put into some message that is sent either through read path to all the caches and whatnot, or through the write mutation path if it's a Starling Assistant read too. Mutations and Starling Assistant reads are treated equally, and they are handled in a certain order that is created, surprise, because it's a queue. The CQRS assumes the queue. And like to me, CQRS is a proper way to think of OOP, unlike other stuff. Okay, I'm going in circles. Moving on. The next one is, I want to talk about topics and partitions. This will, disclaimer, it's too close to Kafka, but it's not specific to Kafka because a lot of solutions these days are adopting Kafka terms. So like this is one of those cases where with all my dislike of Kafka and how it's incorrectly used, I think I used the word abused in the slides, then I rewrote it as misunderstood. So with all the use and abuse of Kafka these days, there are quite a few good things coming out of Kafka, which is people finally start to understand that the throughput of a single vector clock component, which is single partition, is usually the bottleneck. And if you can use more partitions, you can increase your data flow parallelism factor and thus increase your total performance at the expense of having partial order. So I personally would not blame anyone if you guys arrive at this idea of topic partitions through Kafka, even though I think Kafka is just, it's a clever-ish way to introduce these terms. If I will build it, I will build it differently, and I think the idea of consumer groups should not be the first-class citizen in our thinking, in our thought process, but it is what it is. So the way it works, again, I think, given we talked about this for so long, it should be quite clear how to connect the dots. So within one topic, again, I'm talking Kafka terminology, but it's commonly reused by other products too. Within one topic, each message has a sequence ID. Within one topic, for each pair of messages, we can know exactly which one came before, which one came after, or if there's anything in between. The sequence IDs are without holes, 0, 1, 2, 3, etc. Take it back, misspoke. Within one partition of one topic, scratch that. Within one partition of one topic, there's a total order. Within one partition of one topic, there exists the sequence ID. And within one partition of one topic, the message with the lower sequence ID is assumed to have come before and will be processed before the message with the higher sequence ID. Across partitions, even of the same topic, this guarantee is not held. And in fact, you cannot possibly argue that if you have a topic of 4 partitions, there's just no way, unless the user explicitly added some metadata to the messages, there's no way on the Kafka level to tell that message with sequence ID 17 in partition 2 came before or after message with the message ID 31 in topic 3 in partition 3. You just cannot tell that. That's exactly what partial order stands for. Partial partition. So if you need total order, if the order is important for you, use a single partition, or at least choose a partition key, such that within a partition, the order is important, and across partitions, it's okay for the order to not be important. Like, for example, if it's, again, Google Docs, as an example, if the partition key is the document ID, clearly it's okay to not know the exact order of mutations, of changes into different documents. But within a document, that's important. Now, this was just logical stuff. This was first order logic, first principles. Now, second order logic, which is Kafka specific, is the idea of consumer groups. So Kafka lets developers implement the code that processes the data from different partitions. And Kafka is trying its best to give you this exactly once processing guarantee. It's of course at least once, because exactly once is nearly impossible. But the way it works is you build your own piece of code that is invoked on every single message of a given topic/partition. There is a mechanism of acknowledgement, so you get the message, you get the next message or the next batch of messages, you process them, and then you tell Kafka, I'm done with this message. So don't send it to me again, I've processed that. But the idea is that since you want this sequencing guarantee, and since you want it to be as close to exactly once as possible, but realistically at least once, because of this, you cannot assign more than one processor, more than one consumer to a partition. Which means if you have a topic with a single partition, no matter how many nodes you throw at it to process it, it's going to be only one node doing the work, just by definition of how Kafka works. I'm not saying I like this logic, but I think it makes perfect sense, and it makes sense to understand it. Which also means that if you're using Kafka, and if the processing has to be fast, if you need to increase your throughput, the only way, if you're using Kafka, to increase your throughput is to introduce more partitions, which means to break total order. So once you have many partitions, there are extra costs in Kafka if you push into multi-partition topic. So like if a topic has literally like 100 messages per second, for God's sake, like 3 max, like literally not 20, makes no sense. It's just too expensive to write the multiple partitions. But if the throughput is high, or the processing time of the consumer, if the processing throughput per consumer is low, and if you need to process everything, you will have to use more partitions, if only to make Kafka's consumption logic use more consumers. Yeah, now that I said it, I think it's pretty clear. The last bit of this detour is that the way Kafka works is it actually does solve the consensus problem behind the scenes. So again, as a SysDesign primitive, Kafka is pretty genius because you can use Kafka and not have to use etcd, console, zookeeper, or whatnot. Because behind the scenes, Kafka does their job. In fact, it used to depend on Zookeeper, but since about 2 years ago, it does not. It has its own consensus engine built in. And what it does is, if you have a consumer, or other consumer group in this case, potentially more than one machine, once the consumer sends the acknowledgement that for a certain partition, up to a certain message ID, message sequence ID, it was processed, Kafka remembers on the level of Kafka itself that this particular consumer has consumed this message. That's why it's called consumed and not processed. So this is the idea of cursors and offsets. Like, I think now I can speak like totally freely because we have all the terminology. So if you have a single topic, single partition, for each consumer there is a single number up to which index it has consumed the data. If you have a topic of like 8 partitions, there's no single number. There are 8 numbers up to which offset within each partition has your system consumed the data. And this becomes the vector clock. Instead of total order, where the single number is all you need, you have this partial order. And in order to know up to which are you processed, like where are you up to date to, you need to have this vector of n elements, where n is the number of partitions in a topic. And Kafka remembers up to which have you processed for each individual consumer. So if you have a consumer ID, you can reuse it, and then you can restart the consumer, new logic of your code with the new consumer ID, with the same consumer ID, new version of the code. And it's going to start from the same offset that the last instance incarnation of this consumer has confirmed to Kafka. That's the beauty of it. So it's sort of like you could use Kafka as the total order broadcast engine if you have a topic with a single partition. Could be too expensive and could be not fast enough, because the Kafka has limited throughput, especially on this, like per partition. But if you were to build a trivial event sourcing solution today and your traffic is low, single topic, single partition Kafka is pretty much what you need as a primitive. And it's a pretty good primitive if used correctly. Well, I had to talk about this because I think it's an important primitive, both logically and practically. If you like me believe it's too constraining and you can do better, Erlang is probably the best starting point to read about. What do we have left? I'm not going to talk about this in detail. It's a big section of a blog post. Basically, when the system is distributed, you have a lot of ways things can go wrong, and there's a narrow subset of making sure things go right. And this narrow subset these days, the modern day understanding of how to do things right in a distributed setting is oftentimes orchestration versus choreography. TLDR, orchestration, is when there's a logical, like total order of events that happened even though the events took place across the entire cluster, multiple machines, multiple nodes, you sort of pretend them to follow some orchestrated pattern. So this orchestrator itself should not be a single machine because it can die and stuff goes wrong. But logically, it's as if there's an orchestrator. So it's more imperative. The state of this entire system is more explicitly reconstructible, and it's oftentimes linear. Choreography is when nodes can just talk to each other without any leader. Presumably, stuff will work correctly, even though reconstructing the state or the linearizing the path, it may well be nearly impossible because there's no clear before-after relationship. I just want to emphasize that on a happy path, they usually behave identically. But when things go wrong, recovery is extremely difficult in the choreography setting. So like in an orchestrated setting, proving your code is correct, at least logically, is generally trivial. In the choreography setting, I could write some logic, some code on a piece of paper and claim it's faster and better than orchestrated, but proving that is a non-trivial exercise. It's like differentiation and integration. Differentiating is a trivial problem. Integration requires creativity, and there are some non-trivial, no closed form solution integrals. Pretty much the same applies to choreography. So, which is kind of interesting because the topic of the episode today is stateful orchestration. So we pretend that orchestration is the future, even though we all know that the more resilient the system should be, the more likely we'll have to use some choreography behind the scenes. That is super difficult, but that's the way of life. A few more slides, I promise. Disintegrated storage. When people talk about databases these days, you would often hear stuff like, we have multiple nodes for this database. Oh, this database runs on 5 nodes. Well, the thing is that nodes are not created equal, if only because sometimes you need different scalability for different subnodes. The best way to understand disintegrated storage is to embrace the idea that you can have a storage node and a compute node. They're totally different. Like storage node guarantees the data is not lost. Compute node is what stores the indexes so that the queries are fast. And like, if you understand this, you're 90% there to understand the disintegrated storage. But of course, in practice, you can differentiate far further. You can have like all of storage nodes with dedicated indexes, like search index or vector database, lookup index, which is also part of your database, but it's a different type of node. As long as you design your system under the assumption that it has to be done this way, you have integrated storage. The truth is, the good thing is, because we now have this term at our disposal, because we now know what we call disintegrated storage, we can be more flexible in terms of SysDesign, in terms of the boxes to use. We can be more flexible that, hey, let's call this storage, let's call this box a database. Even though we know behind the scenes it's a database with a few dedicated indexes that are super high performance, super effective, specifically at these data retrieval tasks. Before we had this universal understanding that it's okay to call stuff disintegrated storage, you would have to build your own system with message queues, with Kafkas, with like cache invalidation mechanisms to make sure your index is up to date. Today you can say this is storage. It's just a clever piece of storage that contains different types of nodes for different query access patterns. Especially this holds true for combining real-time queries with analytical queries. So like back in the day, a couple of years back, you would say, oh, so this is where the real-time query path is. And for analytics, the data is copied over like every night, and then you can run your Hadoop jobs. That sort of remains the case. It's a crime to load production databases with analytical queries. But you can now say it's part of my storage, which is disintegrated. So I don't care how it's done. My DevOps, my database ops can handle this magic. My system just assumes you have this storage that can be queried both real-time and analytically, which I think is super cool. And I think we're finally at the point where we can talk about the true goal, North Star of today, workflow orchestration. So before we truly enter this, I want to talk about what exists as the concept and as the product today. And that is the product called Cadence by Uber, and now there's Temporal. There's a history behind this. I believe if you Google in a few steps you'll find out that Temporal is pretty much the fork of Cadence taken further by a couple of people. So like to me, they are quite diverged. Maybe not necessarily in the code, although in the code too, but they're quite diverse in terms of what you can use for which purposes. Like if you're an enterprise company, you probably want to use Temporal because they can like offer you business contracts to maintain stuff for you. If you're a startup or if you're an enthusiast, you probably want to use Cadence because it's open source. Like that's just my instinct so far. So the idea is that, like, full disclosure, I'll just be upfront. I think much like with all my dislike towards Kafka became a de facto standard because it solved the right problem. I'm not entirely sure today to which degree I agree with the decisions taken by Cadence and Temporal, but I think they deserve to be, this idea, this concept of orchestration deserves to be the next standard building block in system architecture. And since this meetup is about SysDesign, I think we should talk about that. And the idea behind Cadence and Temporal is pretty much like, let's combine the queue, so to speak, of messages and the power to process those in the setting that is distributed, so that each processing step, each iteration, each piece of logic is guaranteed to execute such that if the machine that did the job died, the user doesn't notice. It just restarts on this place somewhere else. So basically, you used to have to write stuff like compensating transactions yourself because you had to assume that the node that does the execution, that implements certain parts of the workflow, this node can fail. It may have to restart, or maybe it loses its state and some other node has to pick it up. And if something took place that is incorrect, that has to be compensated for, the logic of compensation, of the logic of determining what has to be compensated for, and then running those transactions, that's on you, on the developer. And then, of course, the compensation itself can also fail, so it turtles all the way down, right? Compensation on top of compensation, et cetera, et cetera. What Cadence says is, we're going to let you write the code, and as long as you follow some rules, as long as you abide by certain constraints, we're going to give you a framework that guarantees that this code executes. Strictly speaking, exactly once. That's the claim. But in practice, it's of course not entirely exactly once so far yet. But the idea is that, yeah, if you have like do A, do B, check conditions, if they fail, revert A, revert B, you write it this way, and you know for a fact that if it did enter the revert A part, it will eventually execute the revert B part. It might take a while. It could be a different machine doing that because stuff was dead. But the logic of your code does not need to be made more difficult. All the state of your execution, all the logic is kept consistent by the execution framework of Cadence or Temporal. And the beautiful part of this concept is that once you internalize it, a lot of things effectively become Cadence-ish, Temporal-ish workflows. And which is super interesting because when I first heard of it, I thought of a couple examples, but apparently the domain where the examples fit is just so broad. So because it's an Uber cadence, right? We can talk about Uber. And inside Uber, if you order food through Uber Eats, it needs to be prepared, right? The restaurant needs to accept the order. The restaurant then says the order is prepared, it can be picked up. Some driver gets assigned. The driver may well be making some trip right now. It may well have to make more stops because it has to be optimized, right? Like this workflow has to outlive a single machine. And if you don't have any technology such as Cadence, you'll probably write a lot of, like, you would dump your state to database and you have this event-based code where you have to, like, you wake up, like your daemon wakes up, you go to the database, get the state, and then you decide, what's the next step here? Is it time to dedicate the driver? Is it time to look for the driver or whatnot? With Cadence, you just write the code logically, linearly, A, B, C, D, and then the framework takes care about its execution for you, which is super cool because that's exactly where I started the talk from. We need to make sure that people who do not necessarily understand all the details from the inside can write the code that is correct and maintainable and extensible. And then suddenly, once I realized this, a lot of things came in place because any order lifetime management that could take a long time, like Amazon order, airplane seat, that's also a workflow. If it's stateful and distributed, I'd love to have my team have some framework where the code they write can be linearly explained to a new team member, and the execution intricacies, details of like compensations and whatnot, they're taken care of by the framework. And then suddenly, like orchestrating microservices, imagine you need to migrate your database from A to B. There's tons of steps. You write some code to migrate this node to that node, but you can only shut down this node if at least this many nodes in a new cluster have this data up to date, like atomic swap of source of truth. All this is super non-trivial. It's seemingly a different pattern of business logic compared to like, compared to an Uber Eats order lifetime. But it's same degree of guarantees you need to get from the framework. And if you have these guarantees, your code is far easier to follow. And I have heard multiple stories of different companies using workflow orchestration, Cadence or Temporal, I think most of Temporal these days, for cross-domain payments. Like if your company is in the payment business and you need to like send some data, reconcile send some money across country borders or state borders, or maybe it changes type, like you're paying crypto and these people should get like euros. A lot of this type of work is being done in the workflow fashion, which I think is fantastic. That's the future. I shouldn't go too much into this because A, it's taken a while, and B, I think it deserves its own dedicated episode eventually. But yeah, the guarantee that it's executed end to end, I think it's awesome. Of course, it's not truly exactly once, because if you fail to confirm a step, the same micro step will be re-executed. So again, if you stay inside the system, it's exactly once. Like if your workflow spins up a new workflow, you can be sure that it's spun up exactly once. But if you go like send an email, well, you may have to you may see it multiple times. That's normal. And this example of sleep 30 days before taking the next action, I think is a fantastic example of if you do things right, it's just making so much more sense compared to like event-based, database-based design. So like, yeah, source of truth of certain workflows is no longer explicit in the database state for you to manually parse, but is implicit by the framework execution layer that just makes it work for you. All right. Honestly, I think we should... Oh, no, wait. I'm going to talk you guys through an example as promised, and then we'll stop for today. So it is actually okay. This is okay to talk about because I've heard this from multiple people in different companies. I'm not going to name any company, but it's a real live interview question that people tend to ask these days. Build an ACID database where the only primitive you have to store the data is Amazon S3. S3 is object store, not blob storage. Right, EBS is blob storage. S3 is object store. So you have this black box that has a lot of nines, like 99.9999 uptime and resiliency for the data, but the mutations there are slow. So you can like put some multi-gigabyte object there, but it's going to take a while to write it, and it's going to take a while to read it. And the interview question is, that's the only thing you have to store the data. Now I want a database, as a database, so that like operations such as Edda sends money to Bob, but only if Edda has enough money on the balance, and the get of balances of Edda and Bob is respecting the invariant of the sum of their amounts. It's a large-scale generic problem. And if you did not hear me talk for the past 1 hour or something, you will probably think of a bunch of solutions, a bunch of approaches to this problem. They would likely involve message queues, two-phase commits, orchestration, in-memory state, right? What I'm going to tell you is, if you approach this problem through the lens of workflow orchestration, it's not going to become more difficult, but the solution is going to be so much more generic that by learning how to solve this problem, you will automatically in your head solve a lot of similar problems. And yeah, it's going to revolve around the idea of stateful orchestration. So if you get asked this question, or if I'm asked this question, the first thing I would say, I would clarify, like let's confirm what exactly are the guarantees I need to fulfill, because like ACID database is too broad of a term. And if the interviewer is thinking along the same lines as I am, which often is the case, they would probably Yeah, see Alex. They would probably tell me that certain amount of nodes can be lost, can disappear, and the data must still be there, like up and running correctly. If that is the requirement I need to abide by, then in my head it's already stateful orchestration as the problem statement. In my mind, once I'm there, each transaction for this ACID database becomes a workflow to be respected. So again, without stateful orchestration, the way you would approach this problem is through the lens of consistency. I need to make sure that whatever transaction is being applied across nodes has to propagate properly, and if some node fails, all the state is restored in other nodes. And then we would have to talk about if a transaction is partially applied, who is responsible for making sure it's fully applied? Like if there's a need to compensate for something, where do we store this knowledge? In a different like meta internal table that can also be losing data because machines are dying, all the scary stuff. Or instead we can talk about the workflow. We can say we have a query, and let's talk about the lifetime of the query. If everything goes well, it's executed step by step, and the result is sent to the user. If anything goes wrong, you can restart the query, like abort the previous one and restart it, and your orchestration engine would take care of making sure you don't do extra work, and the result you compute is correct, accurate. So yeah, the solution is that once you apply, as long as you keep applying the query, this life of a query, the lifetime of this execution, the state of this virtual machine, so to speak, that executes the query, will need to live somewhere, logically, not physically, because it has to live across nodes, between nodes. It cannot possibly live within a particular node. So then the component that is responsible for potentially taking care of conflicts being resolved can be boxed down to the component that ensures the correct order of executing the steps of this query workflow, which is exactly what stateful orchestration is about. So what I'm trying to say is that, like, think of the Uber Eats order example. Without cadence, you would need to manually think about how do I encode the state of execution of a particular order. How do I encode it in the database so that when my code wakes up, when I'm notified of the state change, it needs to restore the state, decide on the next step, apply this next step, and move on. With orchestration frameworks, a lot of this state is implicit in like at which part of this code, literally, you're in. Because like you sleep somewhere, you get back to the same line of code. If the machine has died in between and the other machine took over in a couple seconds or minutes, it's still the same part of the code. It's still the same line, same resume point. And that's exactly what stateful execution is about. So I'm not sure if I'm going in circles or if I'm making sense. I hope it's the latter. But the point is that as soon as we have the means to generically convert linear workflows of stuff like Uber Eats order into distributedly executed workflows that can be picked up by any node if the other node failed and executed exactly once, as long as it's all inside the system. And we are all inside the system. It's our own database after all. Then your logic of keep this data in memory, apply transactions here, take a snapshot, put it into S3. All this logic becomes linearly trivial, linearly clear, as opposed to the logic of actually executing the workflow that lives in the engine of executing the workflow. So yeah, that's pretty much about it. I should stop at this slide because that's the plan for today. And yeah, I guess it was too much. Let me really stop here. Maybe take some questions. Sorry if it was ambiguous. I did not do it for real for over a year. Glad to be resuming. Well, I could just...
Yeah,
Yes, please.
quick question, if I may. So first of all, thanks for the presentation. A lot of information condensed. Thank you very much. You put quite a few hours. Maybe hundreds of hours for the presentation. So my question is the following. Even though we keep talking about this exactly once ish guarantee that in practice is not that important, because we know that there are still cases when it's very difficult to maintain that. So I was wondering whether or not, so the cadence, both cadence and temporal, they indeed kind of have this. They promise you that the workflow as a unit would execute end to end, or eventual, right? But there are some multiple steps which are called activities, and those activities they have to be designed in a way that they can be called, they can fail, and therefore they can be called multiple times. And inside of this activity, there still will be might be some side effects that can be executed more than once. So my question is, do you envision, a system, like a framework, that would guarantee that there are kind of really, academically speaking, exactly once systems, steps, no matter what, are those systems are even, demanded in the current, markets, or those systems are just purely academically interested and therefore not viable for like execution, for example, like a startups or what's not. Finished.
That's multiple questions in one. Well, so first of all, thank you, because you introduced me to Temporal to begin with. Look, I do believe that it's an early stage product of the humankind touching on this domain of problems. Yes, I'm aware how activities work in Temporal, and I think it's a hack. It's not how the long-term solution should look like. With this being said, like Kafka, topics, and partitions, in a way, are also hacks, but they became the norm. So to the degree that even I am talking about them openly, telling others to understand how they work, even though I would have done it differently. So on the one hand, I would love it if the world gets to the stage where 5 years from now, we don't need to separate activities from workflows. We have a certain set of guarantees. We have some DSL in which the code is run, and this DSL is giving you certain guarantees. And as long as you're fully within the realm of idempotency friendly API contracts, you are exactly once for real. And I do not see why it's not possible. I think it's inevitable. On the other hand, the pragmatic approach, history tells us that good enough is good enough. So maybe I can see us living in the world where 5 years from now we writing workflows where it's important to know the difference between workflows and activities, because that's what most people are familiar with. Much like topics and partitions and cursors in Kafka, that's something you have to know today, even though ideally you shouldn't have to. So yeah, I cannot make predictions of what the future needs, and I cannot make predictions on what the industry would do. My experience of many years is that if there's a pressing need, a good solution emerges, but at the same time, good enough is good enough. So yeah, that's probably, if I want to do something in this space, I should be fast enough and loud enough. Part of that is my interest. How far this goes, hard to say. But we're going to try hard. Thank you for help and support. All right, let's call it. Thanks so much.